Okay, welcome everyone to this webcast live from the studio of the World Economic Forum here in Geneva, where we will have the pleasure to ask some very experienced and insightful experts to talk to some of the conclusions of this year's Top 10 Emerging Technologies Report of 2025. My name is Fred Fenter, and I am the Chief Executive Editor of Frontiers, the scientific publisher, and co-publisher of this important report. This year's report, the 13th edition, was released last summer at the annual meeting of the new champions in Tianjin. And in Tianjin, we were very pleased to see the report in action from day one, which started with an overflow briefing session on the first morning, and then it was followed by a number of impact hub sessions that brought all the technologies we talked about to life to all the participants at the AMNC. Since the meeting, this report has been incredibly well received. There have been over 300,000 social mentions of the report to date, and the report itself has been downloaded over 56,000 times. The authority of this report stems from the methodology that we employed to curate and the network of experts behind its preparation, as well as the hard work of the International Steering Group that pulled it all together at the end. They selected from the shortlist these 10 technologies from a field of over 250 contenders. Our College of Chief Editors at Frontiers were directly involved in the process, starting with their participation in a survey at the beginning where they suggested some technologies that they felt were adequate for this report. We have an outstanding report this year with 10 technologies that tend to cluster around three general themes of energy, information technology, and sustainability. This year we included two new features, a strategic outlook assessment by the Dubai Future Foundation, which invites readers to consider the implications far broader than just the article that we have on the technology itself. And we published an ecosystem readiness analysis, which evaluates how prepared we are, in society and in terms of our societal infrastructure, in order to take these technologies forward, to scale them, and to achieve their projected impact. Finally, each technology is elaborated with a transformation map as part of the Strategic Intelligence Platform of the World Economic Forum. So you can see the first slide shows the screenshot from the publication space of the Strategic Intelligence Platform of the WEF, and this is an example of one of the transformation maps that we prepared around this technology of green nitrogen fixation. They were prepared largely by experts from our network of chief editors in our scientific journal program. So, as I mentioned, the report is available on the publications platform of the World Economic Forum. And I'd just like to mention that today's session is sponsored by Frontiers Policy Labs, which is a free-to-access online platform that connects scientists and their work to the world of policymakers. So, let's get started. Today, we will explore not only some of the specific technologies presented in the report, but we will also address the emerging technology, the theme of emerging technology from a broader perspective. Specifically addressing the question, how does the research innovation cycle move the outputs of laboratory research all the way to the industrial scale solutions we need to address the challenges faced by society today? So let me now introduce the panelists for today's discussions. We have first Shivkumar Kalyanaraman, who is Chief Executive Officer of the Nanozymes National Research Foundation, the ANRF, a foundation which was set up by the Indian government in a very, very ambitious effort to reform and scale the research and development ecosystem in India, shaping how academic research connects to industry, innovation, and national priorities. We also have Heike Freund, who is Chief Operating Officer at Marvel Fusion, a clean energy startup focused on developing quantum-enhanced laser-based fusion technology aimed at delivering safe, clean, and reliable energy. We're also very pleased to have Javier García-Martínez, who is professor and director of the Molecular Nanotechnology Lab at the University of Alicante. Javier is a world-renowned chemist, nanotechnologist, and entrepreneur whose work in green chemistry and advanced materials is reshaping industry. And finally, we have Karen Baert, who is co-founder and CEO of Ammobia, which is a Stanford-born startup reimagining ammonia production with a disruptive Haber-Bosch 2.0 process that slashes costs to deliver clean ammonia at scale. So let's just jump right into it. And we're going to use a format today where we have just 2 questions for each of the panelists. We're going to try to move through this in a very effective way so that we can leave time for everyone listening to ask your own questions at the end of the presentation. So, Shivkumar, first question for you. In your career, you have virtually seen every stage of the research innovation cycle, from the research lab all the way to game-changing implementations, including the rollout of digital platforms to support sectors of energy, mobility, and advanced IT technology. With the Top 10 Emerging Technologies report, we aim to identify those technologies that are past feasibility tests and are ready for industrial-level scale-up within 5 to 10 years. So, in terms of setting the research and development priorities for India, how do you go about assessing the potential impact of new technologies that emerge from the research and development landscape, and how do you guide your community to direct their resources effectively?
Thank you, Fred. And first, it's wonderful to be here among such a distinguished set of panelists. And, congratulations to the World Economic Forum and the Frontiers Group for such an insightful report. And I hope many more will read it and benefit from it. So, just a one-line introduction about ANRF, Anusandhan National Research Foundation. It's a mechanism set up by the government of India to drive funding into various sectors of the economy. Think of it like the National Science Foundation and a combination of that with an ARPA type of entity. But we also are deploying capital investments, through second-level fund managers in a large program as well, right? So it's a bold experiment to drive and catalyze the research and innovation investments in India. So coming to your question, look, I think we have both horizontal, broad-based investments in research. So where we don't tell the investigators what to investigate, and we get in sort of proposals and we fund them through grant programs. But then when we do vertical investments and pick particular areas of thrust for what we call mission mode programs, we apply obviously a national filter to look at what are technologies that are important strategically for the country to acquire. That's number one. But beyond that, we are interested in seeing not just import substitution and things like that, but really how can we develop new value chains out of India and new economic growth engines for India. So that is one viewpoint. The second viewpoint is a societal viewpoint. What are the big societal problems in India, which we'd like to solve in our market and so on. So the first value chain view is to really look at global markets and where India can play a role and grow the economic opportunity and therefore the employment for our huge and young population demographics. And the societal view is looking to solve India's challenges and problems, but to do that in interesting ways and also which can lead to global impact in terms of whether providing public goods to the globe or a new entrepreneurship that can help the globe. So that would be the way we look at it.
Okay, terrific. Well, Shivkumar, thanks for that. I hope you've had a chance to have a look at our Top 10 Emerging Technology Report. One of the technologies that we honed in on this year is the collaborative sensing. In collaborative sensing, it's a situation where you have distributed sensors in a certain context that are becoming connected and then controlled with AI-infused systems. And for example, this is one where there's a lot of talk about this becoming very useful in the management of urban mobility. what is your professional view? Have we been over-optimistic on hoping that there's a 5 to 10 year window for wide-scale implementation of this type of technology?
I think I would take it in two parts, right? One is the collaborative sensing itself. I think that's an idea whose time has come, and its applications to various areas. I mean, urban mobility being one of them. Its time has come, and that data, IoT data, being a real-time foundation for AI. I think that's certainly an area which is likely to take off. The second part of it is that the applications are not just to mobility. You may have a sensor, a multi-purpose sensor that is mounted on mobility platforms, which may collect information that might be useful for urban mobility itself, like traffic and traffic management and the like. But there could be sustainability objectives. There could be urban flooding management objectives. There could be air pollution and other public health objectives, which could be met by the same sort of multi-purpose, distributed sensing, and also if the closing of that cyber-physical systems loop to actuation, which either changes behaviors or actuation where the actuation can be done quickly, is strong, then I think the adoption can be much faster as well, right? So I certainly believe the answer is yes, but with those caveats.
Okay, Shivkumar, thank you very much. We're going to move now to ask a couple of questions to our panelist, Heike. Heike, you have been a leader in the transformation of industry in several sectors, including automotive, machinery, and high tech, in addition to your current role. Just at a high level, what are the strategies based on your experience that span industries and that decide who wins the innovation race?
So Fred, thanks so much. It's a pleasure to be here. And as you mentioned, I've been fortunate to work across different industries, from automotive to high tech and now energy. And what always strikes me is that the race isn't about technology alone. It's about vision, it's about courage, it's about the ability to bring others along. And that's as true as it is for cars, as it is for fusion energy. So when I look across industries, I see 5 strategies that decide who wins the innovation race. First, it's vision with persistence. So Tesla wasn't the first to make electric cars, but it reimagined the car as a computer on wheels and never let go of that vision. And we now see similar boldness in structural battery composites, as you highlighted in the recent WEF report, where materials come to play that can both store energy and serve as a structure of the vehicle. Second element that I see is cross-pollination. So when you look at the biggest breakthroughs, they often come when ideas jump industries. So carbon fiber came from aerospace and then reshaped the car industry and even sports. And a modern example of that is now osmotic power systems, which generates clean energy from water gradients, taking inspiration directly from nature. Third is ecosystems over silos. So as you all know, the iPhone wasn't revolutionary because of the device alone, but it was because of the ecosystem of millions of developers behind it. And the same principle nowadays applies when we look at AI climate modeling, which only works when really researchers and startups and governments all collaborate globally. Now, the fourth element that I see is a scaling mindset. So innovation isn't just invention, but it's also making it work reliable at scale. So if you look at Siemens or GE, for instance, they transformed industrial machines by scaling digital twins, predictive maintenance, and so on. So really moving away from only selling hardware, but to delivering entire digital services. And fifth, one of the most important one is also courage. So innovation means daring to fail and learn fast. So if we look at SpaceX, I think it's one of the best examples where they actually let rockets explode publicly, but each failure was a step on their progress further. So building a culture where you want leaders to fail fast and learn is super important. So across industries, the winners are not the ones that invent first, but those who combined vision, cross-pollination, ecosystems, scaling, and courage in doing so will be the ones that will transform entire markets.
Okay, thanks, Heike. As you know, we're almost obliged to ask the next question, which is specifically around the advanced nuclear technologies, which was one of the top 10 that was picked for this. So this one's coming. I'm sure you get this question all the time, but can you just give us some insight in light of many of the recent breakthroughs in fusion? How close are we to a commercial solution, and which stages still need to be transformed to get reliable fusion onto the grid?
It's a great question, Fred. And I mean, fusion is often described as the energy of the stars. It's what powers the sun. And if we can harness it here on Earth, it would give us nearly limitless clean energy without long-lived radioactive waste or meltdown risk. So it's exactly what we would need in the energy mix of the future. But where are we today? So in the last 3 years, fusion has clearly moved from science fiction to science fact. We've seen the first experiments that actually produced more energy than they consumed, so namely the experiment at the National Ignition Facility in California, which demonstrated for the first time ever energy gains, so producing more energy out of the fusion reaction than what was put in. But we've also seen major advances in lasers and also magnetic fusion technologies, and we have seen now billions in public and private investments. But let's also be clear, we are still at a prototype stage. I think you can think of it as aviation in the 1920s. We know we can fly, but we still need to build the first aircraft that can actually carry passengers safely and reliable. So what needs to happen next? So I would say there's 3 big areas that need to happen next. One is technology integration. So really thinking about a power plant design, combining lasers, fuels, materials, and everything into one system that actually works on a power plant scale. The second one is industrial scaling, so moving away from single experiments and also building up the whole supply chain and ecosystem that is required to build the whole fusion industry. And the third one is also regulatory and societal readiness, so really creating the frameworks and trust that we need to bring this complete new energy source to the grid. And I think that's also where the World Economic Forum comes in. They've named advanced nuclear technology as one of the top 10 emerging technologies of 2025, which shows fusion is no longer seen as a distant dream, but as a credible near-term innovation challenge. And I think just as the other technologies that have been mentioned in the report, it highlights the real innovative potential that fusion energy would have in the energy mix of the future. So we see a strong momentum. You've asked about the timeline. As the fusion industry, we expect to see fusion power plant on the grids in the 2030s. So there's been a recent study by the Fusion Industry Association where more than 70% of the participants of the fusion industry said that they expect to see fusion power plants on the grid by 2035. So 70% by 2035. I think that is a strong answer from the fusion industry and shows the momentum we have. So fusion is no longer a dream for our grandchildren, but it's a challenge for our generations. And again, the winner will be those who combine breakthrough science with industrial innovation and partnerships, and then really turn fusion into something that we can manage on Earth and bring the sun to Earth and generate fusion energy here.
Heike, thank you very much. And now we'll move over to Javier. Javier, welcome.
Thank you.
The first question, you've been a long-time contributor to this project of the Top 10 Emerging Technologies report, and this year you contributed directly to two of the articles that were published, the one on nanozymes and the other on green nitrogen fixation. But based on your background and all that you've accomplished in your professional career, Can you tell us about current directions of green chemistry, and then specifically in this context of moving from laboratory to a industrial solution? Which of these do you see as gaining traction and being adopted by chemical companies?
So thank you for the opportunity, and it's wonderful to see the impact that the report is having. The figures that you mentioned are really striking. So green chemistry is really a new way to imagine, teach, and do chemistry. And this is very important because it's not only critical for our planet, but green chemistry is also the foundation of the competitiveness of the green future, the green chemical industry of the future. The other thing I want to say is green chemistry has been an engine for innovation. It's striking to see how many discoveries from the lab are now being deployed by the chemical industry by investments exceeding $100 billion. So this is not just emerging. Green chemistry, it's a reality and the foundation not only of the competitiveness of the industry, but also basic and I would say critical for our future. Some trends in green chemistry, I would start by saying electrification of chemical processes. So now we use a huge amount of fossil fuels to heat our reactors. And now we are seeing large-scale projects like the one being deployed in Germany by BASF, SABIC, and Linde to start with the first large-scale electric steam cracker. And that's great because if finally all this electricity is coming from green sources, that will account for reducing 90% of all the CO2 emissions of one of the largest chemical processes. Another one is biocatalysis, and we know enzymes are very good catalysts. So now we are nano-engineering these enzymes to carry out reactions, but now without solvents, reducing waste significantly. Actually, very recently, the chemical company Merck reported that in the synthesis of some pharmaceuticals, they have been able to reduce by 45% amount of waste produced, but just replacing conventional chemistry by enzymatic chemistry. Another big one, I'm sure our audience will be familiar with this, is plastics. We need to reimagine how we make plastics, and companies are really doing that. And I want to mention two examples. One by the chemical company Braskem, we're already producing thousand tons of biopolyethylene, a bio-based plastic, which is significantly reducing the amount of fossil fuels we have to utilized to produce plastic, but even more importantly, we can now turn CO2 into valuable products, and that's what Covestro is doing by incorporating CO2 into the production of polymers. And finally, and I'm sure Karen will be telling us much more about that, green nitrogen fixation, that we decided to include it in our report this year because we have been seeing very large-scale projects around that. I want to mention the one by Neon in Saudi Arabia, which is now 80% completed. And if this finally get to full production, that will mean over 1 million tons of CO2 savings per year. And that's important because when we produce ammonia, and ammonia is not only important for fertilizers, but also to transport and store hydrogen, we're doing it in a way that accounts for 2% of all the CO2 emissions. And that's why, because we also need hydrogen, not only nitrogen to produce ammonia. And that hydrogen needs to be green, and that's the big challenge, but also the great opportunity for the green hydrogen. So just to summarize, there are many trends: electrification, biocatalyst, sustainable feedstocks, green nitrogen fixation. And the good news is that the chemical community, the chemistry community, it's really coming with brilliant ideas, new startups, which are the basis of this new revolution that we call green chemistry.
Okay, thanks, Javier. Since you are the author of the Nanozyme technology article, I have to say that in talking with people over these last 6 months or so about the report, that seems to be one of the more difficult technologies for people to understand, but one that has shown promise in a wide range of applications, from neurodegenerative disease all the way to food safety. So can you just, in a few words, explain what nanozymes are and give us some promising examples about how this technology will emerge as an effective way forward to solve some of these problems?
I know that Nanozymes may sound unfamiliar, very abstract. Actually, I have to say that I was suggesting this technology for a number of years, and very happy to see it now in our report. Even my colleagues from this report were not fully convinced until now, until 2025. The concept is actually very simple. I just mentioned before that enzymes are fantastic natural catalysts. They can carry out reactions, mild conditions with exquisite selectivity, but that's also the weakness. They need to operate under very mild conditions. They're very expensive to make, and sometimes it's just not scalable. So nanotechnology is coming to the rescue. Now we can produce and modify the structure of nanomaterials in a way that they behave like enzymes. That's what nanozyme means. It's a nanomaterial with enzyme-like behavior. And I managed to convince my colleagues because now there are very concrete examples. And one is one example is the one you mentioned, which is absolutely amazing. So now with Syrian oxide, very, very typical inorganic material, we modify the structure and the morphology. This material can reduce the oxidative damage in tissues by more than 45% in clinical trials. And that is fundamental to prevent Alzheimer and Parkinson's disease. And we see that with Syrian oxide, such a simple compound, but by modifying the structure of these materials, we can really see this kind of behavior. Also in food security, with iron oxide, something at rust, something so simple. But if we modify the structure and the morphology of these nanoparticles, now we can detect pathogens like E. coli in a matter of minutes. And even during COVID pandemic, some of the test kits that were used were also based on nanozymes that were much more robust and reliable than the enzyme-based tests. And also for environmental remediation, we are seeing companies now trying to commercialize manganese oxide nanoparticles that are actually efficient in more than 95% in degrading organic dyes in water. So I know this concept of nanozymes may seem a little bit science fiction, but it is a very powerful idea. The fact that we can produce nanomaterials with enzyme-like behavior. And that was a concept, many papers around that. I'm sure Frontiers will be publishing many papers on nanozymes, but now we also see companies commercializing these technologies. And I don't want to go into details about these examples, but they are from commercial trials to clinical trials in different sectors, these technologies being deployed. And if you just want to follow the patterns in nanozymes, that's also booming. And that's what we want to do with this report, really identifying what's the next big thing, what's coming, and maybe introducing a new concept to the audience. So now they will be familiar, I hope.
Terrific. Thanks. So thank you very much, Javier. And we're going to move now to Karen. Welcome, Karen. We're going to start with, as with the others, we'll start with a high-level question. I picked up a quote that you said in one of your communications that many transformative energy technologies have followed the well-known Gartner hype cycle, from hype to post-hype dip to plateau of real impact. Specifically, in your work, can you tell us about the challenges of climbing towards that plateau of real impact in terms of building out infrastructure for green ammonia?
Absolutely, and thank you so much. It's an honor to be here amongst fellow innovators and technology enthusiasts. I genuinely believe that it's disruptive technologies which will enable a cost-effective energy transition and mitigation of climate change. I think that's why we're all here. So let's talk about the Gartner hype cycle to make sure that all listeners are familiar with the hype cycle. So it starts with the hype, right? There's a new technology, there's pitches and PowerPoint slides where you talk about the potential of the technology. Of course, the sky's the limit. And then you have the post-hype dip that typically, especially with hard technologies like ammonia production and many others, There's some kind of initial disappointment, let's say. Why? I think there's a quote that says, like, every hard technology, when you actually build your first project, it takes 2 times longer than you thought, and it's 3 times more expensive than you thought. So there's cost overruns, there's delays, scalability issues arise. Certainly what happens a lot in hard tech climate technologies, and is more of the rule than the exception. But after that post-hype dip, we get to that plateau of productivity, as you said, and that's really where we can realize the full potential. That's really where you can have a repeatable, profitable model where a new technology really shapes and changes a new industry. Now, it does take a while to get there, and it is not easy to get there. And I think there's 4 main reasons for that. The first one is the technical maturity, especially for hard, disruptive new technologies. It takes a while to really reach that maturity. Having a pilot that has some first good results is not exactly the same as having a chemical plant that can run reliably for years, if not decades. The second one is a cost curve. It also takes a while to get to a cost-effective technology, even if you can clearly show that the fundamentals of the technology show that it's going to be cheaper than the incumbent, right? You need to not just prove that it works, but you also need to improve everything behind it, such as supply chains, optimization, and you very often also need to reach a certain economy of scale to be able to get to that competitiveness. And in technologies like ammonia production, that has a major impact. And the third piece is around value proposition, actually proving that it's not just a one-off and not just a cool technology, but that it is actually repeatable and it can create value in a repeatable way. And the last thing I'll mention, which is also really important here, is financing. Again, new hard technologies take a lot of money to scale. And so you need enough capital that is patient, that is willing to take risks, and also often for that kind of slightly later stage financing that does not necessarily expect VC types of returns. So for all of these reasons, it's a challenge. It's hard to reach that plateau of productivity, but once you get there, that's really where you create the step change in the industry.
Terrific. Thank you very much. Thank you very much, Karen. In the report on the green ammonia, it says that the ammonia industry is in transition. And it mentions a number of technological approaches in terms of that are being developed in parallel in order to achieve this goal. Just, we've been talking about timelines. Can you give us an idea of when you think that we will actually hit a real tipping point away from the traditional Haber-Bosch process in ammonia production?
Absolutely. And as Javier mentioned, the ammonia industry is definitely in a transition, and a really exciting transition. Before we talk about what's happening after Haber-Bosch, I think we first need to really understand what Haber-Bosch has meant historically to our world, because there's really a before Haber-Bosch and an after Haber-Bosch. Haber-Bosch process, so the nitrogen fixation process, where you take nitrogen from the air and hydrogen from coal or natural gas and turn it into ammonia, that process has been absolutely changing the world in many ways. It was invented in 1914. And before that, we were fully dependent on natural sources as fertilizers. Once that process was invented, we were able to basically double population growth, because we were and are using ammonia as our main fertilizer. And now, fast forward 2025, the ammonia market is a $150 billion market, and it's feeding half of the world's population for its use as a fertilizer. But yes, indeed, the ammonia market is changing. Why is it changing? We do not only need ammonia as a fertilizer and as an industrial feedstock. We now also need ammonia for the energy world. Very different use cases, right? The reason why we need ammonia in the fertilizer world is actually for the nitrogen content, which is what helps us increase the productivity of our lands. The reason why we need ammonia in the energy world is for the hydrogen content. Why? Because hydrogen is a very powerful energy vehicle, but it is hard to transport and store. And when you turn it into ammonia, it makes it a much more transportable molecule. And so that comes with a range of new use cases for ammonia. Overall, there's an expectation of around 3x increase of the size of the ammonia market, from a $150 billion market today to an up to $500 billion market by 2050. So that's mainly driven by two large use cases. One of them is using ammonia as a maritime shipping fuel. Second one is using ammonia for power import and export, and to a certain extent also power generation, such as co-firing ammonia with coal-fired power plants. So range of new use cases. And so that brings me to like the technology and the technology innovation. Historically, we've only needed to produce ammonia from coal or natural gas at massive scale. And to be honest, for that application, the Haber-Bosch process is perfect, because it runs really efficiently at massive scale. Now that we need ammonia for different use cases, we need more ammonia, and we also need to be able to produce ammonia in a green way, so without leveraging fossil fuels. We really need to think about alternative technologies, and that is really the reason why there's such a change in the ammonia market. So I don't necessarily think there's going to be a completely kind of a tipping point completely away from Haber-Bosch anytime soon. I do think that we're going to start leveraging a wide range of new technologies that will be a better fit for different applications. Specifically, any locations where you want to produce ammonia locally at smaller scale, then you definitely need innovations to Haber-Bosch. And the second key one is anywhere where you want to produce ammonia from renewable resources, such as producing ammonia from renewable energy by leveraging green hydrogen. So with that, there is, I think, three big buckets. I know the report mentions many more that I want to highlight in terms of innovations to the Haber-Bosch process. One of them is basically electrochemical approaches. So Haber-Bosch is a thermochemical approach. Electrochemical approaches can be really effective for smaller scale ammonia production. And some of them are really interesting in the sense that you can turn water straight into ammonia. So normally with Haber-Bosch, you have two steps. You turn water or fossil fuels into hydrogen, and you turn hydrogen into ammonia. So of course, a one-step approach comes with advantages there. The second kind of bucket are kind of a range of really innovative ways of looking at ammonia production, such as plasma-based approaches. A lot of these show a lot of potential, but kind of they're earlier in terms of technology readiness level. And the third bucket I'd mention, and that's the one where Ammobia operates in, is innovations to Haber-Bosch. So we call our technology Haber-Bosch 2.0. These are just innovations to the thermochemical ammonia production process to make it lower cost, to make it require less energy, and to also make it more flexible or rampable, so you can run on renewables in a more cost-effective way.
Terrific. Thank you very much, Karen. We have about 5 minutes left, and there have been a few questions coming through. There are three themes that are evolving. So people would like to hear about the role of AI in these various contexts. People are talking about the fact that there is a very strong link around energy. Energy seems to be tying all of these different themes, together. And personally, I really liked the word that Heike came up with, courage, and the fact that there is a human element in terms of taking technology from the laboratory into the innovation space and then into a industrial development. Let's try to see if we can get to all three, but let's go backwards. So let's start with the word courage and the human dimension in taking emergent technology to an industrial scale solution. Shivkumar, I don't know if does this resonate with you, for example?
Yeah, I think the competitive advantage of nations is directly linked to technology diffusion, and the rate of technology diffusion is ultimately a human process along with the innovations that technologies provide. And this is a very fragile process. So often, especially in some of the bold innovations that have been talked about in this meeting, courage is is absolutely essential, whether it's from the courage of the funding agency, courage of the first entrepreneur, and the persistence that comes along with the courage. I think one of the interesting opportunity is that with AI we can really accelerate the deep science to deep tech journey much faster, and I think hopefully that will help accelerate this and become one more dimension along with the absolutely important human quality of courage and resilience.
Thank you very much, Shivkumar. Is there somebody who'd like to jump in on this theme? Okay, Javier, or would you prefer to address the AI question? So you have your choice.
What I would say is last year, actually, we selected AI for scientific discovery, and that links so well with what we are discussing today. One, because in the discovery of new catalysts, either for green ammonia or for nanozymes, AI is already producing significant advances and is really helping us to discover new materials that they are so much needed for the energy revolution that you have been mentioning, but also for the green chemistry trend that I was mentioning. The chemical plants produce a lot of data. Now every chemical plant is fully digitalized, and it's only through machine learning that now we will be able to operate the whole complex system that a chemical plant is. That's not only one process, multiple processes which are interconnected if we use machine learning and AI to optimize how chemical plants are functioning. That's a big challenge, but I think it's also a great opportunity for running chemical plants in a much more efficient way.
Thanks, Javier. And I'm going to sneak the last question. We haven't touched upon energy. I know this is a very accelerated question and answer process here, but Heike, we were chatting the other day, and I pointed out there was an Economist article that suggested that there isn't enough energy to power all of the chips that NVIDIA is currently manufacturing. Energy is a bottleneck, I think, in a lot of the different the technologies that we've talked about today. So last word about the role of energy in terms of making societal progress.
Yeah, I mean, it's a super important aspect, right? So one could argue that AI is the first technology that humanity invented for which we don't have the energy source yet. Because if you look at, there are some predictions of that the US needing by 2030, I believe, more electricity for data center than France consumes today in terms of electricity. It actually shows that there's entirely new countries basically popping up on the world in terms of electricity demand. So we will clearly need a lot more electricity in the future to run AI. However, I will also see the true innovative potential that AI has. So I see that in fusion and so on, we use AI also to discover new materials, to run simulations faster and so on. So I think it's something where I think Sam Altman actually invested in a fusion energy company, and he said AI needs fusion and fusion needs AI. And I think that's true for many technologies, as Javier just pointed out, as well on the chemistry side. So I think, yes, humanity needs AI to proceed with all the different innovations that go further, but we also need energy for it, and especially electricity, and that's really what's holding the world together, electricity. So we need more electricity sources, and fusion could be one important aspect in that picture, but obviously there's also a lot of other activities, whether it's geothermal or other technologies. So I think we need all of them, and there's a lot of activity happening right now.
Okay, thank you very, very much, Heike. And I think I have enjoyed this discussion so much. It's hard to believe that it's already been 45 minutes. But it's time to thank our panelists today, Shivkumar, Karen, Heike, and Javier. Thank you all for participating. And I do hope that we have the opportunity in some other context to continue these very, very interesting discussions. So thank you very much, and thank you all, everybody, for taking part today. Thank you.